So today we're going to do recommender systems. So essentially Netflix and Co. And I have to say great thanks to Yehuda Koren, and probably about 20% of the slides, maybe 25% of the slides are courtesy of his, at least some of the diagrams and so on from the set of slides. So if those of you who don't know Yehuda Koren, he is one of the guys who won the Netflix prize. So this is about as much from the horse's mouth as you can get it in terms of recommender systems. So let me start with some basic ideas. So recommender systems, we all probably know them from Netflix. They really popularized it. And the issue is basically, you have thousands of movies and maybe TV episodes and so on, and you want to determine which ones you're going to pick. So, basically which ones are you going to take, and you want to order them, and maybe I really like action movies, but then it still doesn't make sense to show me only action movies here. You might want to have a bit of diversity, and what you really need to do is you need to come up with a good idea of how users really interact with your web property. So there's a lot of user modeling, targeting, collaborative filtering, and so on. This all really forms the heart of a lot of interesting internet services. So that's basically what we're going to do today, recommender systems. And with that, you can probably do better than a lot of the startups that are currently building related systems. So I'm going to start with something very simple, namely simple neighborhood type of methods for recommendation. And they're useful and important for two reasons. First of all, they're actually some of the oldest methods out there. Secondly, they're actually not too terrible. So if you use a simple recommender method based on neighborhoods, it's something that you can put together very, very quickly, and at least you'll have a baseline of a product demo that you might want to build. Matrix factorization is, well, considerably more powerful, and so I'll talk a little bit about the similar value decomposition style factorization, why it's actually interesting, and then more importantly, how you can actually solve it at scale, and we might very briefly touch upon things like convex reformulations eventually. Fairly important part of this is, however, also the entire aspect of session modeling. So the issue is basically that you don't just want to know which movies are really popular with the user, but you also need to figure out how to present that content to a user, how to reorder them. So I'll show you a little bit the things that you need to watch out there. And there's an entire industry essentially of people who work on this. In the end, we'll talk a little bit about features and about hashing. So this is incomplete. That you could probably teach an entire class on recommender systems, but I hope that it'll give you a little bit of an idea of some tools to look at. Another technical piece of information. So on April 17th, Deepak Agarwal is most likely going to fill in for me. The reason for that is that I will be in Lyon at the World Wide Web Conference, and I'm sure that Deepak is going to do an excellent job. So he's the guy responsible for much of the Yahoo front page content personalization. So he has a lot of experience in how to build such systems. In practice, the content of his class is still a little bit to be determined. But yeah, so you can rest assured that it's going to be exciting. So, why do you really care about it? So, we have all those movies, Netflix, and you want to find out, which ones should you show. And the fact that this is really a grab bag at the moment is more a testament to the fact that I canceled my Netflix subscription, and now it just shows me the unpersonalized recommendations. But even in that case, you would wonder, which movies should you actually list up here to get people's interest. This is a little bit too personalized. So this is actually me being logged in, and I'm looking here at a specific movie that I haven't watched yet, but what it then also does is it recommends me related movies that I might potentially be interested in. Now this is not exactly collaborative filtering personalization, because it hasn't really gotten any explicit feedback from me yet. But the point is that it knows my past viewing history, that I'm logged in as you can see on the top, and it knows which movie I'm currently looking at, so it might be a good idea to guesstimate that I might be interested in related movies to this. So that's what, essentially the Amazon Prime and also then the Kindle recommendation system would be using. Then same thing you can do not just with movies, but you can play this game with books. And here it tries to actually recommend books for me, and the recommendation is pretty good. So those two books I actually have sitting on my bookshelf. This one I don't, because I don't use R very much. Of this author I have a similar book. And it actually says it in the bottom, recommended because you purchased nonlinear programming. Right? Here it says also nonlinear programming. So at the moment it and here Bayesian non-parametrics, that's why it thinks that Bayesian data analysis is interesting. And that's actually not such a great recommendation, but what it tells you a little bit is also how the algorithm comes up with these recommendations. Now the obvious question is, how do we build such algorithms which A, come up with related recommendations, and B, which can explain why they do things. Here's another example of essentially collaborative filtering and recommendation, and this is one that you probably wouldn't have thought of as explicit recommendation. So here I'm logged in on my Google News page, and for whatever reason it's decided that this is the top story to show me, and then a few other things. What you can see down here is actually things that are probably more specific to my viewing behavior than anything else. So here's, for instance, some German news. In this case, I actually had to enter in the profile that I'm interested in German news. And this is probably more based on my viewing behavior, possibly also because I need to read the New York Times a lot. So there is some degree of personalization going on, but probably not a massive amount. And it's very much implicit, because in this case, the query is essentially Alex goes to Google News and tries to and wants to read relevant content. So it's not a very specific query. If I then were to expand, let's say for instance a story, that would correspond to something now much more specific, where I'm interested in stories along these lines, and I want to find related news that I'm interested in. Here's another example. This is from Yahoo, and well, to some extent this is apparently personalized. Since I don't read these articles very much, I mean, you can't really blame it very much for the fact that it thinks Kim Kardashian is really an important person for me. Okay. Another example of recommender systems is, to some extent, is spam filtering. And at the other end is the priority inbox, right? So the priority inbox are those emails that are really important. And I'm not going to show you what's in there, but I'm going to show you what's in my spam folder. And you can see that something went very much wrong here, because the UCB Warn Me account was instantly considered spam without me ever seeing it. Okay, that's not my assessment, but maybe there's some, must have had some reason for that. Again, it's essentially a content recommendation system, and the fact, for instance, that I opened the screen, that I looked at this, and that I then decided that, okay, well, I'll leave this email there. You can actually treat that as a signal that I'm probably sort of okay with what happened. Okay, so let's take a slightly more formal view of things. Because, I mean, usually when you talk about, collaborative filtering recommender systems, you only think of two things, namely, there's a user and there are objects, and collaboratively we decide which objects to look at, and what our rating is going to be. But actually this is only a very small part of a much bigger picture, because you have a context. The context may be the device on which I'm, viewing the site. So for instance, I could be viewing the site on a tablet. I could be viewing the site on a mobile phone. I could be viewing it on a netbook, on a high-end laptop. I could be viewing it on a desktop with a 24-inch screen, or on a TV. In each of those cases, my willingness to go through a fair amount of content may be very different. So for instance, if I have, a mobile device, then I have to reformat things very differently. I can't really have all those side tabs and so on, and I want to have reasonably large font and will scroll through very quickly. And I can probably also log where I've scrolled to. Whereas on the 24-inch screen, well, I probably won't want to have a single pane layout. I might want to have a 2-3 pane layout with various sections, subsections, and a fairly rich structure. So that's why the context actually matters. And the other thing is, it depends on where I am. So for instance, if I'm traveling overseas on an expensive data plan, also what time of the day, also what time of the year. So for instance, if it's around Christmas, well, we all read more Christmas stories and, probably, click on, ads with, overweight men in a red dress. And then lastly, with the interface itself, in what modality I'm actually going through the site. So one thing to recommend, so there's this custom feature Phoenix, it's a very good custom maker nearby, and it was quite interesting when I went there last time. The owner was surfing the web on an old computer with Internet Explorer with a fairly large number of toolbars and other browsing add-ons installed. And there were ads and other things, and so out of the XGA screen, which is 1024 by 768, she probably had an active usable viewport of maybe 300 by 400. And she was having a lot of trouble actually really consuming the content based on that. Now, that's bad user experience on her end, but what it also tells you, if you're providing content through that you can be pretty sure that she didn't even see all the things that were suggested to her. So the fact that she didn't interact with some content is probably more due to the fact that, well, she just didn't even see it in the first place, rather than her not liking it. So what it really means is that, we have a display interface in which we provide the content, where we select the objects, where there's a certain context, and for a particular user. So one thing that you would have, for instance, noticed, and I've been told so by designers, web page designers, that for instance in the Middle East, if you design web pages for that part of the world, pictures are really important. Whereas if you go to, let's say, a Korean or a Japanese or a Hong Kong web page, you will find lots and lots of text, very densely packed, very tightly packed, and not a lot of big pictures. And while North America is somewhere in between this. So there's clearly a very strong cultural bias in terms of what content you like, what content you're more used to. Also screen sizes and so on really vary by country. So you want to adapt this based on all these contexts. So a couple more examples. Well, we already know movie recommendation for Netflix is like a typical example for content recommendation. Related products. Web page ranking is essentially also, by now, you could think of it as a collaborative filtering problem. Because based on what I will click on, well, the search engines will re-rank and update their search results. It was probably about a year ago, a bit of a storm in a teacup, where some Google engineers supposedly created a sting operation against the evil Bing search engineers, and basically what they did is they created a fake query with fake results. And they ran this on some machines which they called honeypot machines, and they had the toolbar, the Microsoft toolbar installed. Now what the toolbar does is it basically logs the URLs and the pages that you're viewing and sends it back to Redmond. Or well, probably to the Silicon Valley lab, I don't know which one, but basically, let's say, for the sake of the argument, it sends all these logs to Redmond. So basically, the service at Redmond logged that for certain queries, certain pages were clicked on. Okay, so it's perfectly reasonable to use that data to improve your queries. After all, when you install one of those toolbars, they come with all this fine print, and somewhere in the fine print it says, and by the way, I will send all the information about what you're doing to the corresponding entity. So this is why you can get lots of toolbars. By the way, Chrome, depending on which version you install and with which configurations, will do the same thing and send it happily to Google. So I think there's the pot calling the kettle black. But basically what happened is, I mean, all this information got incorporated into Bing's index, and then at some point they issued this nonsensical query into Bing, and out came the very same search results as what Google had created as a quote sting operation. While this was very nice then played out by journalists in the news, essentially all it just meant is it showed for everybody how much user activity data is used to improve search results. And why shouldn't you? Now, so use content recommendation, a lot of places do that by now. Priority inbox and spam filtering, these are essentially the opposite extremes of the really important emails and the really unimportant ones. And yeah, Google does Yahoo, AOL, whatever. Online dating to some extent have a similar setup. So depending on the website, they will either ask you tons of questions and try to see who correlates with whom best. It doesn't quite do the, well, people who went out with this person also like to go out with that one, even though that sometimes would be interesting information. Yeah, so in a way this is also a collaborative filtering problem. So the reason why I found out that some of these things exist is because once upon a time Yahoo was also in that business, and it turns out that it actually owns one of the patents, and I know about that fact because the co-inventor of the patent has the same last name as I do, but I've never met him. No. So, yeah. Now, the other thing is computational advertising. Again, you're essentially trying to recommend, well, somewhat vaguely relevant content to the user. I mean, what's better than an irrelevant ad? Well, an ad that you might actually be enticed to click on. So, you want to show a user relevant ads, and so to some extent, the notion of whole page relevance has quite some meaning in, search results or overall what you present to a user, because a user will come to your site because of the overall experience that you get from the site. In other words, it's the totality of news articles, ads, how useful the interface is and all that, that makes a user decide whether you, for instance, use Bing or Google or Yahoo or AOL or anything else. So that's why it's in your interest to increase the relevance of the ads as much as you possibly can. Furthermore, well, you also want to make as much money as you can, and if you show relevant ads, the users will click and you make money. Okay. So our running example for today is largely going to be Netflix movie recommendation and later on some user modeling for news. So the data on Netflix looked pretty much like that. So there were some user IDs, movie IDs. There was actually some information about the name of the movie, but that was that. And there was a date attached to it. Then a score. And then the test data was essentially of the same form, except that the scores weren't revealed. And as you can clearly see from here, the scores went between 1 and 5. And they were integral scores. So the obvious challenges were scalability. So when the data set first came out, people didn't quite know how to handle data at that scale very well. So I remember us sitting down and discussing, okay, how can we make it actually fit into a machine and all that. And what you really have is millions of objects, maybe hundreds of millions of users, if you're one of the major players on the internet. And some of the issues are, for instance, cold start. So if a new user comes along, what they recommend him initially. And to some extent, that's actually one of the most important things, because that new user, if he doesn't see relevant content, will be gone again. The other thing is that the inventory keeps on changing. So in the case of movies, well, new movies are released, sometimes new products are released, and if I'm on a news site, well, actually, the news articles will change. And, you know, the last thing is that actually you have a fairly imbalanced data set. In other words, there will be some objects which have a lot of reviews and some which have very few. And likewise, some users will be extreme busybodies in actually reviewing things. So we saw that, for instance, last week, like 2 weeks ago, when I showed you the personalized spam filtering data, where the number of reviews per user decayed very rapidly. And the same thing we saw last week in the context of couch surfing, where there was also a power law type graph between number of requests for a particular couch and couches.
What is the x-axis on the picture?
Okay, so these are, okay, that's number of ratings per movie, and that's basically just ordered by number of ratings.
Okay.
Okay. So actually you should have probably sorted it the other way around, but okay, they didn't for whatever reason. So here's an early post about 6 years ago, about, or 5.5 years ago, about what to do with a Netflix data set.
But that basically means all the ratings are really concentrated to some.
Correct.
Okay.
So there are basically some movies that are really popular and everybody rates them, and some of which are essentially unknown, except for a few people who really like them. And yeah, so I mean, this is so those type of power law behaviors you find in a lot of natural data, and you find them in graphs where the number of edges per vertex can be correspondingly distributed. Some sites take action specifically against it. So for instance, Facebook, I think, only allows you to have, I think, at most 5,000 closest friends and caps it at that limit. Twitter clearly doesn't. So this is how, you know, Justin Bieber ends up with, I think, 3 to 4% of the entire bandwidth. Well, Facebook has sort of also worked around it by allowing, you know, larger entities to have a product page, and you can friend or follow that product page, and there's no limit to how many people can do that. So in a way, they've just taken this power law graph and said, okay, everything up above here is, you know, commercial, everything below there is a normal user. And yeah, that's in a way a rational way of categorizing this. Now, what people usually do in Netflix is they use a least mean squares prediction error as the yardstick. So in other words, you look at, you know, the actual ratings, look at the estimate, take, you know, the sum of the, you know, square differences, and normalize by that set size. And that's the root mean squares error. So this is basically the thing that everybody was competing about. And effectively, this is a, I mean, while this is very nice for the purpose of the competition, because you can, you know, write it in one line and everybody gets it right away, it's really the wrong measure. So let me show you why this is a really bad idea. Suppose I really like Die Hard. Okay. So, but I also like other movies. So now if I were to only use this RMS, you know, only pick the highest ratings, then of course all the Die Hard and harder and hardest movies will, you know, come up on top, but it will not show me anything else. So on any day that I don't feel like watching Die Hard, I'll be really stuck. It'll suggest, oh, you like Die Hard so much, well, here's another one. So clearly something's going very wrong here. The only good thing really about this score function is that it's consistent. In other words, if I try to, you know, minimize the score, if I in the large sample size limit, my estimator will converge something that is fairly accurate. Now, there are a lot of other loss functions, and for instance, Moon, I mean, so he's the guy sitting about, yeah, in the middle there waving his hat. So he's done a lot of work on looking at different loss functions for ranking purposes, and I think he pretty much wrote the definitive paper on that, comparing, I think, about 10 different of them. The sad news of that is, you know, tweaking those loss functions helps you. It helps you quite a bit, but not as much as you would think. Probably picking a better model, looking more at the context, will actually help you more than, you know, tuning your loss function even further. So, in other words, 10 years of loss function research probably gave about a 2 or 3% lift overall. So, you want to do better than that. Anyway, now, here's the first thing that you could do if you want to do just collaborative filtering, and here's the basic idea. So, Yehuda made those very pretty slides. So here's the idea. So Joe wants to watch a movie, and Joe has watched those 3 movies and rated them in some way. And well, you know, these movies were also seen by maybe these 3 people, and these 3 people watched some other movies of their own, and then I had some opinions of these movies. And so the question is, you know, what other movies should Joe watch? Well, what you can do is you can simply follow through which of the other ones were most watched with corresponding ratings. And then you pick the ones that are most highly rated accordingly in his 2-step neighborhood. So we're going to formalize that a lot more, but this is essentially the graph equivalent of a nearest neighbor type method. So we take user-user similarity to recommend the items. I mean, you would do that if the item base is much smaller than the user base. And it's also good if the item base changes very rapidly, because then, you know, item-item similarity is not a very reliable measure. Now, you would take the item-item similarity, and that's actually the more popular thing, if the inventory is smaller than your user base. Because then the item-item similarity is going to be more reliable than the user-user similarity. The user-user basically means you recommend stuff that other users also liked. Item-item similarity means, well, I'm going to recommend items that had similar ratings from other users. So, subtle difference. Basically, in one case, I decide, well, you know, maybe Mohammed's taste in movies is the same as mine, and so I'll just ask him which movies he liked. In the other case, I look at all of you, and since I maybe liked, I don't know, Sleepless in Seattle 5 very much, then if anybody else of you also likes Sleepless in Seattle 5 and then some other movies, I basically look at all the movies that are very similar to Sleepless in Seattle number 5. I don't know whether there's such an issue, but they surely must have made several remakes of it. Then, you know, these are the movies I would then suffer through. So this is actually the oldest collaborative filtering method, and okay, let's just look at it in a little bit more detail. So let's say these are the items, these are the users, and you know, everything that's yellow I know the rating, everything that's white, well, I don't. So suppose I want to know, you know, whether user 5 likes item number 1 or what his rating there might be. Well, what I can then do is I can just, you know, decide that, you know, most similar to item 1 are going to be items 3 and 6. The other ones are not very similar, but items 3 and 6 are quite similar. And, well, they have a score of 2 or 3 respectively to this guy. So, given that movie 1 is very similar to movie 3 and movie 6, and the user didn't really care very much for those 2 movies, maybe he won't care very much for that one. So, now let's, you know, cook up some similarity between item 1 and item 3, and item 1 and item 6. Okay, let's say 0.2 and 0.3 for the sake of the argument. And, well, then I just compute the weighted average. So I take 0.2 times 2 plus 0.3 times 3 divided by 0.2 plus 0.3 to make sure it's properly normalized. And so I got the score of 2.6 out of it. Now, obviously the question is, you know, where do we get those numbers from? And I'll show you that in a moment. And also, you know, why is it going to be exactly those 2 movies, which, you know, relates a little bit to, you know, how do we get those scores? So, as already suggested, well, this is fairly intuitive because you can do things like other users who looked at that movie also like that movie, right? This is easy to then justify why you're recommending things. Basically, it doesn't require really any training. Really, if you think about it, this is where we are, these are the neighbors, the blue ones are the next ones out, so I want to find out, you know, what the score of this one is, given that I know all the blue ones. And it's very easy to explain to a user. It handles new items and new users very well, because as soon as I add them to the graph and they start watching stuff, I can easily propagate the information through. But it's not necessarily very scalable because you have to do actually a lot of lookups, and it's not terribly accurate. So the question is, how can you improve this type of neighborhood-based method? And so we're going to stay with these neighborhood-based methods for a while, go through them in a fair amount of detail, and then we'll move on to stuff that's considerably more powerful. So, and you would have probably actually experienced similar things at a conference. So who of you has submitted a paper to conference and was very frustrated about the reviews? At least half of people in the audience would have had that feeling. So, I mean, what you want to find out, of course, is, in this case, about movies or otherwise about in conferences, is that some items are really significantly higher rated than others. I mean, these are the ones that you really want to accept at a conference, right? But some users rate substantially lower. So some referees are really nasty and they think, everything is boring and I can do everything better myself, so I'm going to rate everything down. And woe be you if you end up with a referee like that, because he's really going to kill your score. That is, unless you actually calibrate for the fact that this referee is a really tough one and he likes to rate everything poorly. Now, the other thing is you want to deal with the fact that maybe some ratings change over time. Well, you can't really do that for a conference, but you can do that for movies. So, for instance, after a movie gets an Oscar, typically the perception of the movie goes up quite a bit, even though the movie may not have improved. So basically what we really need to do is we need to correct for bias within the neighborhood. So the idea is to have, like a common offset. This is just, what the average rating of the movies is. This is the average happiness of a user with with movies in general. And this is, how good that movie is inherently. There's no personalization really going on. It's just that, how much of a, grumpy reviewer I am and how great the movie is in its own right. So, okay, that actually explains that in a fair amount of detail. So, let's take an example. Let's say the mean rating is 3.7, and maybe Troll Hunter is a really good movie, right? But the user really doesn't think about movies so highly at all. So in that case, well, we take 3.7 plus 0.7, okay, minus, in this case, 0.2, and as you can clearly see, I got the math wrong, it should be 4.2. That's why I don't release slides beforehand. Now, how do we actually get those baselines? Well, a very simple thing would be to say, well, after all, we want to do really well in our recommendation system, so let's just adjust those baselines in such a way that the prediction error is minimized. So actual ratings, I sum over all the pairs of where users actually rated something, and I, subtract the baselines. And then I, penalize the coefficients a little bit, because by default, I want the biases to be 0 for both users and movie. And the higher I crank up lambda, the smaller these coefficients will be, and the more I'm just going to get the mean. Now this is jointly convex, which is a nice thing. So you can just, for instance, just cast a gradient descent over it, or you could iterate and just, remove the means throughout. So for instance, if I look at the optimization problem in the BIs, well, that's actually very easy to solve. going to show you that on the whiteboard. So what happens for the PIs, right? So for the entire sum here over U and I pairs, the only users that really matter are the ones who saw movie I. Right? So I only have to sum over all the users that actually saw movie I. So I'm summing over RUI minus mu minus BU. And the average of this, suitably normalized, is going to be exactly PI. And likewise for the user. Okay, so let's just actually write that. Apologies, I don't have a black or a blue pen. Somebody keeps on removing all of them. So let's just take the derivative with respect to PI. So, of course, of the entire sum over I and U, can you guys actually see anything here? See right round, no, whiteboard left. Yeah, the lights are slightly burned out too. Okay. So actually, over all those pairs, the only ones that matter are the ones where the users actually saw it. So I have to sum over all U in R of I. And since I'm taking the derivative, I'm getting 2, well, in this case, R UI minus mu minus BI minus BU. And since it's all a minus, I have a minus up here, then I get plus 2 lambda BI. And this has to vanish. So the good thing is I can already kill off the 2's. And then I go and pull out all the BI's. So that gives me lambda plus size of R of I times BI equals sum over all users in R of I R UI minus mu minus BU. Now you just go and divide by that, and voila, you have the first equation. You get the second one exactly the same way. So there's really nothing special going on. All we do is we just average, and then we iterate. You have to iterate because removing the mean here doesn't actually immediately remove it there, and once you remove it there, you need to correct for this a little bit. But that converges very quickly. It's very, very cheap.
We have a really big RI or RU.
Well, so if you have a really big RI, that's actually a good thing because then it will be pretty much, then it will be essentially exactly the mean. If the RI is very small, that's exactly where you need lambda. Because otherwise, even a single review will already squish everything towards that specific rating. So you're absolutely right, the interplay between the size of the set and the regularizer matters rather dramatically. Otherwise you would overfit.
You're differentiating with respect to BU, right?
Yes. So with respect to BU, I get the same expression here, just that now I, all the I's and U's are swapped. So it's exactly the same algebra. So you think of this derivation, just replace the I's and U's. There's no difference otherwise. Okay, I haven't shown you how to get the mean with respect to mu, but that's tricky. You just pick the mean rating. And in that case, since it really shows up everywhere, you don't really need to regularize it at all, because if you have a million ratings, how much overfitting can you do? Basically nothing. So here's how we could do it in Parzen Windows style collaborative filtering. So we go and compute those residuals the RUIs. And then, assuming that I have some clue of how to get those similarity scores, and we'll get to that in a moment, well, what I do is I sum over, if I want to find out whether user U likes movie I, I'll take, the bias that I will get between user U and movie I, or BUI, and then I sum over all the corrections of, movies that, were also rated by users who also rated, movie I. And I just look at these, at the difference between the actual rating and the bias, times the similarity between, movie I and movie J. So this is really the neighborhood here of movies J that are similar to I, and in this case, just for computational convenience, I only pick the k nearest one. Then of course, to normalize things, I just need to sum over all those weights again. Very straightforward. Basically the same thing as what we did in Parzen Windows, I think in lecture number 2 and number 3. So there we had the following expressions. Remember, so this was basically Watson, Nadaria. Where we had that y hat of x was given by the sum over all x prime k of x and x prime times y prime, the corresponding y for the x, divided by the sum over all x prime k of x and x prime. So that was the Watson and Nadaria estimator. Now, these functions here, these kernels, are now being replaced by the coefficients Sij. The only other convenience is that we decide not to sum over the entire graph, but just over the k most similar movies to this movie, or likewise over the k most similar users. That's the main difference between Watson and Nadaria, which actually had a potentially fairly large scope, and here what we do for collaborative filtering. This already works quite a bit better. So just adding the bias makes a big difference. So of course I still haven't told you how we get the item-item similarity. So one useful way of looking at that would be to say, well, let's just check for any users who rated both items, how strongly, their scores are correlated. And that will be quite useful because if every user who liked this movie also liked the other movie, and likewise everyone who disliked the other movie, you know that, I can easily transfer the ratings from one movie to the other one. So here are two movies, and they have, related ratings. So I take the intersection of the domain, and then compute what's called a Pearson correlation. The Pearson correlation is nothing else but the covariance between the scores divided by the standard deviations for each of them. And you can clearly see that if they're perfectly correlated, this would be 1. If they were perfectly anti-correlated, this would be -1. 0 means they are unrelated. Now, the issue, however, is that, this is, that support may actually be quite small. So first of all, you need to really intersect on the users who've watched both movies. And if there are only 2-3 users who watched both of them, then you're in a lot of trouble. So this, for instance, wouldn't help you very much to, let's say, define a correlation between Die Hard and Sleepless in Seattle, right? Well, maybe it would, but for other social reasons, but basically people who would watch Die Hard would usually not watch Sleepless in Seattle unless their partner drags them into the respective movie.
Or like foreign language films, right?
Correct. So that's actually a perfect example. For foreign languages, very few users would rate would rate movies in two different languages. However, actually in this case, you're running into another problem, and that's much more significant. Because the kind of people who would watch movies in more than one language is a very special kind of people. I mean, they are either immigrants or they are highly educated people who, have the time to, learn more than one language to the extent that they can watch those movies. Now, those people would tend to rate movies differently from people who only speak one language. So there you have now two effects. You have small support and you have what one calls covariate shift, basically where the distribution of the data set that you can use for labeling is quite different from some of the distribution that you want to apply this to afterwards. So, I mean, for movies, the good thing is that you can still assume that you might have a sizable user base in in that specific other language, but it's generally a problem. This, for instance, occurs as a real problem when you want to do web page ranking, and you say have some data for, let's say, maybe the US English market, and you want to build a system that works well in Mexico. Then you would have very few people who search, maybe with Spanish, you would still have a fair number of people who search in both languages, but there may be very different people from what people appreciate in Mexico or what they appreciate if they only speak English and not Spanish. So you have covariate shift there as well. Okay. Now, what you do in order to deal with this, limited support is you basically try to discount all the movies where the joint support is very small. You just shrink it to 0. So let me show you what that means in more equations and less words. So here's a empirical Pearson correlation. So we're just taking a rating minus bias, rating minus bias for all the pairs that were actually watched. So you basically sum over all the users that actually watched both movies, and you just look at the variance in that case for the first movie and you the second. And an interesting happy smoother would be to say, well, we take that Pearson correlation coefficient and then we make some function up front which gets smaller, the smaller the number of users is. And that's really the only criterion which converges to 1 if that set of users goes to infinity. And that function happily does the trick for us. Basically says if there's only one user, well, you're completely screwed. If there's more than one user, well, okay, that function will depart from 0 and converge to 1 in the limit of large numbers of users. The specific functional form is not very important. Furthermore, the specific choice of x is also something where probably heuristics is more important than principled design. So people empirically found that if you take those coefficients that I just showed you and you square them, it works better. Then some people said, well, we can square them and then push them through some sigmoid, and they found it works even better. And yeah, this is basically what happens if a lot of people work on a specific method for a specific data set. The modifications become increasingly unexplainable. Okay. But basically, this is what you do here. The other thing that you can do for the rating itself, so rather than just taking our Watson-O'Dwyer style smoother, where we divide by exactly the same number of, basically by the same mass, I could say, well, if that support is very small, in other words, if the point is really far away from anything else that I've seen, well, I don't want to trust my score very much, so I would just add some small constant to the denominator, such that if this becomes really tiny, essentially it all goes to 0. Or in other words, that all goes to average. This ensures that if I'm really not confident about my rating, I'm not going to proclaim anything that's horribly wrong. I'll just say, well, it's somewhere in the average. Okay. Yes?
So in the extent that you're using kind of this joint support thing where everything
Yes.
kind of shrinks to zero, don't you have kind of an issue with cold starts there? Because like say the
Absolutely.
Die Hard and Sleepless in Seattle, right? Say maybe I would have really liked them the same, but because so few people have done them, you never show them
Yes.
to me, and then I never rate
Exactly.
them.
You're spot on. So there are actually two issues about this. So there's the issue of cold start. If I don't have much data, my estimates may not be very good. And people have written tons of papers on cold start, and I'll show you, I believe, a slightly more principled way of dealing with this. The other thing is, well, once I have those ratings, it doesn't necessarily mean that these are exactly these exactly prescribe the order and the selection of items that I should show you. So, for instance, I might decide to show you, some movies that I'm just not very sure how much you're going to like them. Because unless you ever see them, well, you will just, narrow more and more down to, that small set of, choices that you initially made. So this is sometimes also known as the filter bubble. And so exploration algorithms to some extent deal with this. So, a real life example is, of course, if you go to the New York Times, you will probably see very different positions argued from what's in Fox News. And an avid Fox News listener will probably not have a very open mind to whatever is argued in the New York Times, for better or worse, right? So they basically only get the news that they are most happy with, and this has a self-reinforcing effect. And that's exactly what you want to avoid with some of the collaborative filtering algorithms, because they basically otherwise just create lots of Fox News equivalent stations on Netflix or Amazon or whatever. And that's at least not good for business. So just to conclude with these filtering methods, those similarity-based algorithms. So for binary data, obviously Pearson correlations are fairly meaningless because, well, if we know that the user viewed something or clicked on something or purchased something, well, we know he did it, and there is not much variation within the fact that he did it. So another way of measuring similarity would be, for instance, I compute something like a Jacquard similarity, and you can easily see what that is. Let's say I have two sets. Then one way to argue how similar those two sets are is how large the intersection is, right? And if you look at the Jacquard similarity, that's exactly what you get. It counts number of items in the intersection divided by the number of items in number of events for item I, number of events for item j, minus the intersection. So that's really that entire set here, right? Because this is mij, mi, mj. And then to ensure again that we don't overfit, we smooth with some small coefficient alpha. You can do things like look at a ratio between observed and expected items, and so basically observed items are mij, mi over m is the probability that I happens, mj over m is the probability that m happens, so multiplying that out by m, take that number is what would happen if both things happened independently. And then again, you smooth it a little bit to push everything closer to 0. And, there are lots of other hacks that you can do by, emphasizing infrequent users over frequent users. So it's better if there are a lot of users who watched movie I and J, as opposed to a small number of users who have very strong opinions about them. So I think that's probably a good place to stop, because we are now essentially done with the neighborhood-based methods. Any questions? Go ahead.